Matías viene de Holanda. Su charla la propuesta estuvo tan buena. Nosotros nunca hemos aceptado repitentes, pero estuvo tan buena que dijimos, bueno, lo traemos desde Holanda porque queremos que todos vean esto. Entonces, por favor, un aplauso para Matías y los dejo con Matías.
Gracias. Parce, or whatever you people say. Yeah, hi, nice to meet you. I'm Mathias, and it's good to be here in Medellin. I'd like to point out that I'm not presenting from my own computer, and also apparently I'm presenting from Firefox today, which is interesting, because I work on V8, which is the JavaScript engine that is part of Google Chrome, and Node.js, amongst other embedders. So there we go. Of course, we love browsers of all kinds. And this is the proof of that, I guess. So yeah, today I would like to talk about some of V8's internals. And although these internals are rarely directly exposed to web developers, understanding how they work can help explain why certain code patterns are more efficient than others. So let's just dive right into it. JavaScript objects can have arbitrary properties associated with them. And the names of these properties can have any Unicode character in them, even the non-ASCII weird ones like emoji. But one of the interesting cases that a JavaScript engine can choose to optimize for are the so-called array indexes, which is numeric properties, more specifically integer properties. And in V8, array indexes are handled specially, although in many circumstances these numerically indexed properties behave just like other properties. V8 chooses to store them separately from those other properties for optimization purposes. Initially, V8, and internally, V8 even gives these properties a name. They're called elements. So think of it this way. Objects have properties that map to a value, and arrays have indexes that map to elements. It's just the name that we use internally. And what I'm going to be talking about today is this thing called elements kinds, which I know is a super confusing name because of the double plural there, but it's just another one of those things. This is the name that we give this thing internally. So just bear with me. Now, while running JavaScript code, V8 keeps track of the kind of elements that each array contains. This information allows V8 to optimize future operations on the array specifically for this type of array content. So for example, when you call reduce or map or for each on an array, V8 can optimize those calls based on the elements kind of the array. Take this array, for example. What kind of elements does it contain? Yeah, I can tell you're all JavaScript developers because everyone says number, which is correct. At the JavaScript language level, if you ask typeof for each of these values, you would get number and nothing else. But the interesting thing about V8 and other JavaScript engines is that under the hood, we can be more specific than that. We can distinguish integers from floats and doubles, for example. So the elements kind for this array in V8 is packed SMI elements. Now, for now, don't worry about the packed part. We'll get to that in a second. We'll just focus on the SMI part now. In V8, the term SMI stands for the particular format that is used to store small integers. And the range of a SMI is actually pretty large. It also depends on the architecture that you're using. It's signed 31 on 32-bit systems. It's signed 32 on 64-bit systems. But all you need to remember is that any integer that you tend to use in JavaScript is probably well within the bounds of this SMI range. Now, if you later add a floating point number to that very same array, it transitions to a more generic elements kind. So under the hood, the kind changes to packed double elements. Adding a string literal to the same array changes the elements kind once again. Now we end up with packed elements. V8 assigns an elements kind to each array. The elements kind of an array is not set in stone, as we have seen. It can change at runtime. And in this case, we transitioned all the way from packed SMI elements to packed elements. So let's recap. So far, we've seen 3 distinct elements kinds. There's SMIs, there's doubles, and there's regular elements. And note that a double is a more general variant of SMI, and regular elements are another generalization on top of doubles. Or another way to think about it is that the set of numbers that can be represented as a SMI is a subset of the numbers that can be represented as a double, and so on. So what's important here is that elements kind transitions can only go in one direction. You can go from specific, so types at the top, like SMI, to more general types, like packed elements at the bottom. Once we reach packed elements, we cannot go back up to packed double elements, for example. That's just the way the system works in V8. Now, going back to that array that we had before, the array contains 5 items at this point. But what happens if we assign a value to an index that is far outside of the bounds of this array? For example, if we assign a value at position 9 in the array. Well, this creates holes in the array at positions 5 until 8. The array is now sparse, or holy, as we like to call it in V8. Creating holes in an array downgrades the elements kind to its holy variant. So in this case, we went from packed elements to holy elements. Now, there are many other ways to create holes. For example, you can use the delete operator on an indexed element in an array that also creates a hole. Or you can just not initialize the value of an array when you initialize the array. That also creates a hole. But why does V8 care so much whether there's holes in the array or not? Why does it care enough to have a separate elements kinds for these holy variations? Well, let's find out by taking a look at an example. Imagine you're getting the element at index 8. What's the value for the element at index 8, right? Well, from the perspective of the JavaScript engine, there's a lot of work to be done before you can answer that question. V8 starts off by doing a bounds check on the array index. So once we get a number and we know that it's a valid array index, we check, is the index between 0, inclusive, and the length of the array, exclusive? In this case, the bounds check succeeds, but we still cannot answer the question of what the result is. More work is needed. So the next step is to look up the property named 8 on the array itself. But in this case, that property doesn't exist because there's a hole. That's all that's there at this position. So we still cannot answer the question, and we have to dig a little deeper. Now, because the property is not present on the array itself, V8 has to walk up the prototype chain until either a value is found or the chain ends. So first, it checks array.prototype, which in this case doesn't have a property named 8 defined on it. At this point, we still don't know what the answer is. We continue to follow the prototype chain. So the next step is to check if the property named 8 exists on object.prototype, which in this case also isn't true. So in this case, the prototype chain ends after reaching object.prototype, but it could be longer in case someone extended it. Now, because the chain ends here, we cannot continue searching for this property, which means we can now finally answer our question. The hole at position 8 in the array is undefined. Ta-da! Now, from the JavaScript engine's perspective, that's a lot of work just to get an undefined value, right? If you compare that to a packed array, which is an array that is guaranteed to have no holes in it, it's actually much more efficient to do this there, because you don't need all those extra checks. If the array index is within the bounds, the engine can already return the value, and no other checks or expensive lookups on the prototype chain are needed at all. Now, even if we get a property that does exist on a holy array, then still we need to do a bit more work. The engine still needs to check if the property exists first. So V8 checks if the index is within bounds of the array, and it is, but it still doesn't have enough information to answer the question and return the result. We must check if the property exists on the array, just in case there is a hole at this position. In this case, the property exists, so we can finally return its value. But that's still one more step than compared to a packed array. If the property didn't exist, then it would be a hole, and then we would be back in the situation we were before. We would have to do the whole prototype chain lookup, which is a very expensive operation. So this is the very best case scenario for a holy array, and it's still one more operation compared to a packed array. So in general, packed arrays are preferred over holy arrays. Operations on packed arrays can just be optimized more aggressively than operations on holy arrays. For optimal performance of these array operations, avoid creating holes in the array whenever you can. Now, going back to that list of elements kinds that we saw before, we already knew that there are smice, there's doubles, and there's regular elements. And we also knew that you can transition from smice to doubles and to regular elements. But it turns out there's actually two flavors of each of these elements kinds. There's the packed version and there's the holy version. And we can also transition from a packed kind to its holy counterpart. So instead of these two pyramids, it's actually easier to think of elements kind as a lattice. And this is how V8 implements the system around element kinds and the transitions between them. More concretely, it looks something like this. So we have our SMI, our double, and our regular elements there, and each of those comes in two flavors. There's packed and wholly. And for each unique elements kind, V8 can apply specific optimizations when performing operations on the array. Whenever you're using for each or map or reduce, for example, V8 can optimize those calls based on the information it has available about the array's elements kind. We have a set of optimizations for packed SMI elements. We have another set of optimizations for packed double elements, and so on. So it's not that necessarily some of these operations are better than others, it's just that they're all different. But in general, it's fair to say that more specific elements kinds allow for more fine-grained optimizations. Now, in total, I think I just lost the signal here. Yeah. Anyway, I can keep talking for a while. There we go, yeah. Problem solved. Probably shouldn't have even mentioned it, right? So V8 currently distinguishes about 20 different elements kinds. There's many more than just these. These are the most common ones. And each of those comes with its own set of optimizations. Now, the thing to remember here is that you can only transition downwards through the lattice, so you can only follow the arrows. This means that once a single floating point number is added to an array, it is marked as double, even if it later consists of SMIs only. And similarly, once you create a hole in an array, it's marked as wholly forever, even if it becomes packed later. And as we saw, in general, more specific elements kinds enable more fine-grained optimizations, at least in theory. The further down the elements kind lattice you are, the slower manipulations of that object might be. And so for optimal performance, you should avoid needlessly transitioning between these elements kinds to less specific types. You should try to stick to the most specific one that's applicable to your situation. So let's look at another example here. This piece of code creates an array of length 3. But what does the array contain? Well, I think you know the answer now. The array just has 3 holes in it. The array is sparse at this point, so it gets marked as wholly SMI elements, because that's the most specific possibility given the currently available information. Now, let's assign a value to position 0 in the array. Oh, wait a minute, that's a string instead of an integer, so the kind transitions to wholly elements. Now we assign a value to position 1 in the array. The elements kind remains unchanged in this case. And finally, we assign a value to the last position in the array. At this point, all 3 positions in the array are filled, so the array is packed and no longer sparse. However, we cannot transition to a more specific kind such as packed elements, for example, because of the way the lattice system works. So the kind, unfortunately, remains wholly elements. Once an array is marked as wholly, it's wholly forever. So in this scenario, a better solution is to use an array literal instead. If you know all the values of the array beforehand, you can just use a literal like this. And that avoids going wholly for the array, which means that all the operations on the array will be optimized in a more efficient manner. Free sound effects. Okay, so let's just ignore all that. Okay, cool. Is this thing on? Yes, it is. All right. So getting back to those arrays, right? If you don't know all the values for the array in advance, you can create an array and later push the values to it. That way, holes in the array are avoided, and the array will never get marked as wholly. So this approach ensures that V8 optimizes any future operations on the array to the best of its abilities, basically. In general, life is easier without holes. And V8 can deal with packed arrays more efficiently. So in general, if you need to perform lots of operations on an array and you want to optimize those operations, avoid creating holes in it. Similarly, you should avoid reading beyond the length of the array. Trust me, there's nothing there. This is a very similar case to hitting a hole, although it's not exactly the same. So for example, don't write your loops like this. This loop reads all the elements in the array and then one more. It only ends once it finds an undefined or null element. I didn't actually make up this code example. This is a pattern that is common in jQuery, and they actually do have kind of a reason to be using this. It has to do with old Internet Explorer and their weird DOM behavior. But in general, doing this is a bad idea for your loops in general. This is just as bad as hitting a hole in an array. In this case, V8's bounce check fails. The check to see if the property is present on the array fails, and then we need to do the whole prototype chain lookup again, just like hitting a hole. So don't do this, and instead keep your loops simple and just keep iterating until you hit the last element. Another thing you could do instead is to just use for off. And this works whenever the collection you're looping over is iterable, which is not just true for arrays, but also for things like node lists in the DOM. For off is actually my preferred method of iteration. But for arrays specifically, you could also use for each. And the good news is that nowadays, these three different approaches, so whether you use your own for loop, where you check the length and iterate through all the elements, or you use for each, or you use for off, they're all equally fast. Like the performance should be about the same for each of those different things, depending on what you're doing exactly, of course. So in general, avoid reading beyond the length of the array, because doing so is just as bad as hitting a hole. Now, just yesterday, we actually made this less slow in V8 because we saw real-world code using this pattern on arrays and strings. So this is not as much of an issue as it was before, but it's still slower than not doing it. And of course, reading beyond the length of an array is still considered to be an anti-pattern. There's no point in doing so if you can avoid it. So avoid reading beyond the length of the array. Doing so is just as bad as hitting a hole. Another piece of advice when it comes to elements kinds is to avoid transitioning to a less specific elements kind whenever you can. This is harder than it seems. For example, just adding -0 to an array of small integers is enough to transition it to packed double elements. This is because -0 cannot be represented as a SMI. Any future operations on this array will now be optimized in a completely different way than they would be for SMIs. That's just one more reason to avoid specifically the value -0, unless, of course, you need to explicitly differentiate between -0 and +0 in your code, which you probably don't. But the same thing goes for nan in Infinity. They are represented as doubles, so adding a single nan entry to an array of SMI elements transitions it to double elements. Now, if you're planning on performing lots of operations on an array of integers, consider normalizing -0 and blocking nan and infinity values whenever you're initializing the values and adding them to the array. This way, the array sticks to the packed SMI elements kind, and the one-time normalization cost of doing this can be worth the later optimizations of the array. In fact, if you're doing lots of mathematical operations on an array of numbers, you should probably look into using typed arrays. We have specialized elements kinds in V8 to deal with those as well. And they do this automatic kind of clamping of values, and yeah, it's much better to do it with type arrays in this case. But in general, if you need to perform lots of operations on an array, try sticking to an elements kind that is as specific as possible so that V8 can optimize it as much as possible. Now, some objects in JavaScript, especially in the DOM, look like arrays, although they aren't proper arrays. It's possible to create these array-like objects yourself, as I'm doing here. This object has a length property, and it supports indexed element access, just like a real array, but it lacks array methods such as for each on its prototype. It's still possible to call array generics on it, though. So here we're calling the array for each built-in on the array-like object, and everything works as expected. However, this is slower than calling for each on a proper array, which is highly optimized in V8. So if you plan on using array built-ins on this object more than once, consider turning it into an actual array beforehand. And here we're using slice to do just that. Of course, there's a one-time conversion cost that comes with converting it to a real array, but this one-time cost can be worth the later optimizations, especially if you plan on performing lots of operations on this array. Now, the most common example of this is probably the arguments object, which is an array-like object. When you call array built-ins such as for each on this, then it works, but it won't be fully optimized the way it would be for a proper array. Now, in ES 2015, this new feature called REST parameters can help you with this. They produce proper arrays that can be used instead of the array-like arguments objects in a very elegant way. So nowadays, I think there's no good reason to use the arguments object directly anymore. Just use REST parameters instead, and you avoid the problem altogether. This is not a real crocodile,
and it's not going to have the same performance as a real crocodile. And the same thing goes for arrays. In general, avoid array-like objects whenever possible, and just use proper arrays instead. Now, after all this talk about elements kinds, you might be wondering how to identify the elements kinds of a given array. This might come in handy when you're debugging a performance issue, or just when you're trying to get a better understanding of what I've been talking about. So, luckily, whenever V8 is built from source, it produces a binary called D8. And the D stands for either debug or developer. No one on the V8 team really knows what it stands for. But what it does is it makes it really easy to run some code directly in V8. So to find out the elements kinds of a given array, you open your favorite shell, you build V8 from source in debug mode, and you run a debug build of D8. It's important that it's a debug build, not a release build. You pass in the allow native syntax flag, and doing so enables access to some internal V8 functionality in JavaScript. And entering that command opens up the REPL, the read eval print loop, where you can start to enter some code. So first we create the array that we want to test, and then we call one of those special V8 functions on it, in this case, debug print. And you see how the name starts with a percentage sign? Yeah, that's not really valid JavaScript. We shouldn't use this kind of stuff in production code, and for all these internal V8 functionality that we expose through JavaScript, we prefix it with a percentage sign to avoid people from actually trying to do this. It's only useful for debugging anyway, and it only works in this particular D8 configuration, only in debug builds, so it's not going to work on the web. But still, you can use it locally to figure out this kind of stuff. Anyway, running this code prints a lot of output, even more than what is shown here. But in this case, what we're looking for is the elements kind, which is listed on this line. And in this case, holy cow, the elements kind is holy smy elements cow. Now, the cow does not refer to the animal. It stands for copy on write, which is another internal optimization. Don't worry about that for now. That's a topic for another presentation. But just let's recap now, because we've explored what elements kinds are and how they work. And as a result, we were able to identify some practical tips that can help boost performance. First is to avoid creating holes in arrays. We also shouldn't access indexes beyond the array's length. Try to keep the elements kinds of your array as specific as possible by sticking to a single value type for each array. Avoid using array-like objects, and when you have to use them, consider converting them to proper arrays before performing any expensive operations on them. Now, although this presentation covered V8 internals, these tips don't just apply to V8. Other JavaScript engines can benefit from them as well. And I promise you, by following this advice, I promise your code is not going to get any slower in any other engines. If anything, it's going to get faster across the board. Thanks for listening.